Hello, in this video we're going to look at the Taylor series error-bound. Taylor series error-bound theorem, a Taylor polynomial is defined as Pnx equals fa plus fa prime over 1 factorial times x minus a plus f second derivative of 2 factorial times x minus a squared. So this is the Taylor polynomial expansion. Okay, so the Taylor polynomial for n plus 1 term, which is Pn plus the next term. So Taylor error-bound theorem is assume that the fn plus 1, this n plus 1 derivative exists and continuous, and can be a number such that all the derivative fn plus 1 is less than or equal to k for all the mu between a and x. Then the error between the polynomial and the function itself, the polynomial expansion and the function, because when you use Taylor polynomial to approximate, that was an error, right? The error is less than or equal to k times x minus a to the power n plus 1 over n plus 1 factorial. K is the maximum value of the n plus 1 derivative in the range between a and x. So let's look at an example. How are we going to apply this theorem to estimate the Taylor polynomial? So that Pnx equals Taylor polynomial fx equals ln x at a equals 1 as c is bigger than 1. Show that ln c minus Pnc is less than or equal to c minus 1 to n plus 1 over n plus 1. Okay. We know that since fx minus Pnx, which is less than or equal to k times x minus n to the power n plus 1 over n plus 1 factorial, where k is the maximum of the n plus 1 derivative and x is between a and c. Okay. So in this case, we want to find out the derivative, the n plus 1 derivative. Fx, I have an absolute value. Fx equals ln x. So f of the first derivative equals x to negative 1, which is 1 over x. F second derivative, that equals negative x to negative 2, which is 1 over x squared with a negative sign. Third derivative, which is negative 2 times 2, which is positive 2, x to negative 3, which is 2 over x to the power 3. We keep going. The fourth derivative, which equals 2 times negative 3. So it's 2 times negative 3 times x to negative 4. That give you, you can use 2 factorial. The next one, there was a 1 plus 1 times there, but we just didn't write it out. You can see that that's a negative 3 factorial of x to the power 4. If you keep going, you would know that fn plus 1 derivative equals, well, that would be negative 1 to the power, first is positive, so it's m. Second is negative, okay, just n. Okay, so n equals n plus 1, and then this is even term is negative, but we don't really have to worry about that. N factorial of x to n plus 1, because in the end we add absolute value. The maximum of absolute value of negative 1 to the power n, which is positive 1, no matter what that power is, when x is from 1 to another number, we know that when x is 1, it has maximum. So the maximum number is n factorial. So we know that k is n factorial. Plug it in. So we know that the fx, which is lnc, minus pnc, that will be less than equal to n factorial times c minus 1 to power n plus 1 over n plus 1 factorial. Reduce the n factorial n plus 1 factorial, we have lnc minus pnc, that is less than equal to c minus 1 to n plus 1 over n plus 1. Okay, that's the first one. So second, find a value n such that ln 1.5 minus pn 1.5 is less than equal to 0.01, which means we need to solve a number. Like we know that c equals 1.5 in this case. Okay, you plug it in, so you have c. You have 1.5 minus 1 to power n plus 1 over n plus 1 is less than equal to 0.01. So you just try to solve 0.5 to power n plus 1. This is the exponential function, less than equal to 0.01 times n plus 1. You want to find out the n here. You can use the graphing calculator to graph this number here. This is like this, and 0.01 is positive, pretty much like here. At some point, this is over that. You want use graphing calculator to find out what this point is. Okay, so if you use a graphing calculator, you can see that n, when n equals 4, this 0.5 to power 5 is less than 0.01 times 5. Okay? So the answer is n equals 4.